Let's look at complex numbers, where we're going to perform computations involving complex numbers. In this case, we have this imaginary part, and this occurs when you try to take the square root of a negative number. So by definition, the square root of -1 is I, and by definition, I squared is -1. And then we will see that these can even be, we have a real part to this equation, and then, or I should say expression, and then an imaginary part. So some functions have zeros that are not real numbers. The complex number system is used to find these zeros that are not real numbers. When looking at a graph of a function, if the graph does not cross the x-axis, then it has no intercepts, and thus it has no real number zeros. So for example, if I want to work through these problems, remember this up here, that I can actually bring out an I. So the imaginary square root of -7, I separate it to the square root of -1, and so you can see the process to get my answer. Now be sure to notice that I is not under the radical. And then you just do the same thing for each of these. And if you can break down the square root, certainly break it down. All right, now leave the C, D, and E for you to practice. All right, a complex number, once again, is in this form where A is said to be the real part and B, I, okay, this, because it has the imaginary, is the imaginary part. So you may be asked to do some type of calculation, such as adding, subtracting, multiplying, and dividing. We can add and subtract. You can think of the imaginary number like terms. It's not a variable, but you can think of it like a variable, because that's what you want to do. You want to collect the imaginary part and then the real part together, and then you simply simplify it. Same thing with negatives. Just be careful that you distribute the negative sign, and then once again create the real and the imaginary part. Multiplication is good to remember. The I squared is the -1. So when you're asked to multiply, if I multiply these two square roots, I can pull out the -1 on both and then multiply. Take the square root of 16 is 4, the square root of 25 is 5. I have an I times I, which is an I squared, and then 4 times 5 is 20. And so the I squared becomes -1, and I get my final answer. I can multiply even like two binomials. So the same thing with your FOIL. And then you just have to remember at the end, the I squared, -1. So this is why this became negative. And then collect like terms of the middle terms. Same even if you're squaring here. This is also FOIL. So FOILing it out. And then just don't forget your I squared at the end, and then collect any like terms. And so you can even simplify powers. And so it says here, recall that -1 raised to an even power is 1, and -1 raised to an odd power is -1. So simplifying powers of 1 can then be done by using the fact that I squared is -1, so I squared is -1, and expressing the given powers of I in terms of I squared. So this goes back to, remember, if you have the same base, you add the exponent. So I cubed can be broken up into I squared times I, and then you take the I squared out to become -1. You're just left with I. You can see the same thing here. If it's to the 4th power, we can write this as a power of a power, and then this inside becomes -1. And then you can see to the 5th, we kind of do the same thing up here. The odd powers, separate these. This becomes that power, and then we get I. Now note that it says the powers of I circle through I, -1, -I, and 1. Okay, so they will just cycle through those powers. So if you know that, then you don't really even have to break break these down too much, but again, as you'll see here, I'm breaking down powers because I want to get something squared, and 2 times 18 is the 36. This piece right here becomes the -1. Even power becomes the +1, and I get the I. Same thing with the 58, but so nicely 2 times 29 is 58, and I get my value. And so we can use all of this stuff to come up with what they call a conjugate. And a lot of times this happens if you divide by an imaginary number and you want to get the imaginary number out of the denominator. So we call these complex conjugates because they have a real and an imaginary. And you can see what all that happens is the imaginary part here, the sign on it changes. So anything with imaginary changes. So if I wanted to multiply these two values, notice that this is the conjugate. And so what happens when you multiply them out so nicely, you end up with an actual number. And so this is where I stated a lot of times you will see this used in division. So if we want to divide these two, 2 minus 5i over 1 minus 6i, we could do this by multiplying by the conjugate of the denominator, because that will get rid of the imaginary in the denominator. And so if I go through the steps and multiply this all out, kind of the key is to get the denominator as a number, no imaginary. And then the last step is we just simply separate it to keep it as the real plus the imaginary piece.